Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start with lecture number 24th. Now in this lecture we will discuss about the advanced procedures. In our previous lectures we discussed about the procedures, how we can define procedures and how we can call them. Now here we will discuss about some advanced topics. Before starting the lecture number 24th, we will review what we did in our previous lecture. In our previous lecture, we discussed the assembly implementation of shift and rotate instructions. We discussed about logical and arithmetic shifts, which include shift left, shift right, shift left and shift arithmetic right instruction. Before discussing the lecture number 24th, we will review what we did in our previous lecture. In our previous lecture, we implemented the shift and rotate instructions. In this shift and rotate, we discussed about the logical shift and arithmetic shift instructions, such as shift left and shift right, shift arithmetic left and shift arithmetic right, rotate left and rotate right, and so on. And then we discussed about the rotate along with the carry left and rotate carry right, and shift left with destination and shift right with destination. After that, we discuss about some applications of shift and rotate instructions. Then we implemented the multiplication and division instructions. That there was multiplication instruction, then signed integer multiplication instruction, similarly division instruction, and the signed integer division, and so on. So this is review about our lecture number 23rd, what we did in that lecture. Now here in this lecture, this is the outline, the topics that we will discuss in this lecture, which include local variables, what are local variables and how we can use local variables inside the procedures. Then stack parameters, like how we can store parameters inside the stacks, like registers and stack parameters. What is the combination or what is the difference between the stack and register parameters. Then we will discuss about the invoke directive, then procedure directive, proto directive, and so on. Then how we can pass parameters or how we can pass arguments inside the procedures. So passing by value or by reference, we can pass arguments by reference and by values. And then parameter classification, what is the classification of those parameters. And then we have some examples about these procedures, like exchanging two integers. If we want to create a procedure that exchange the value of two registers or two variables, and so on. Then troubleshooting tips, and so on. After that, during this lecture we will discuss about memory models. This is review what we did in our previous lectures. There was one lecture in which we discussed about memory models like flat, small, tiny, and so on. Then language specifiers. After that, explicit access to the stack parameters, how we can access the stack parameters explicitly, and passing arguments by reference and creating local variables. Before going to start the lecture, there are some terminologies that will be used during the whole lecture and maybe in the coming lectures. These terminology includes what we call these procedures. Either we call them procedures, functions, methods, and so on. There are different names. These programming languages use different terms to refer the subroutines. Now in C or C++, the subroutines are called functions. However, in Java, subroutines are called methods, and in Microsoft macro assembler, these subroutines are called procedures. Now during this whole lecture we will call these subroutines as a procedure. Then there are two terms which are very important, arguments and parameters. So these two terms mostly some lectures they are used as interchangeable. However, there is some difference between these two parameters, how we can differentiate. So the arguments are the values that are passed to the subroutine, by a calling program. So when we call a subroutine in a main program and we pass some parameters, these are called the arguments. So we pass some values or variables or addresses to the subroutine or to the procedure. So these values or addresses or something that we pass are called arguments. And then the parameters, when the procedure receives those values or these addresses or whatsoever, these are called the parameters that are received by the subroutine. Now, first of all, local directive. What is this local directive? A local directive is when we define a local variable or when we create a local variable, it's used and destroyed within a single procedure. So when we define a local, first of all, we have the main program. Here you can see this is the main program. Inside this main program we call a procedure. So maybe here is a procedure. Name of this procedure is A, and we call A. If we call A, then it means we are calling this procedure A. And here if we define some variables, these variables are local variables and their scope is limited to this procedure A. Now these are called the local variables and they are created and destroyed within the procedure. The local directive declares a list of local variables. So by using this local directive we can create or we can declare new local variables that will be used inside the procedure, and they will be deleted or removed when we exit from the procedure. So this local directive immediately follows the procedure directive. Means you can see the example here. We will discuss about the example, and each variable is assigned a type. So the syntax is a local and then there is a variable list. So each variable, so this local directive immediately follows the procedure directive, and we have variable 1 and then its type is here, and variable 2 and its type is here, and they are separated by these commas. And when we define a type, it is followed by the semicolon sign, the colon sign, and there are 3 variables here. You can see first variable is a byte, second variable is the word type, third variable is the signed double word type, and so on. So these are the local variables. They will be used inside the procedure and they will be destroyed or they will be removed or from the memory when we exit from the procedure. Now this is one example. Here you can see there is local directive. You can use, definitely the procedure directive is immediately above this local directive, and we have one array of 20 bytes and its type is byte, and this is array of bytes. Similarly, or you can define local. We have p array or pointer array. This will hold the address of a word type. So this is in pointer to an array, and here you can see another example. We have my procedure. My procedure and its type is procedure, and then there is one local variable is t1 and it's of type byte. So if you want to use procedures, if you want to use local variables inside the procedures, so local directive will be used, and local directive must immediately follow the procedure directive. So this is the Mason generated code when we use local variables. For example, the bubble sort procedure is here, and this bubble sort is followed by the local directive, and there are 2 variables. One is temp double word type, and second one is called the swap flag, and this is of type byte. And then there is a body of this whole procedure, and the last instruction is the return instruction, and this is the end of the procedure here. Now when we write this type of procedure, what type of code will be generated by the macro assembler? So this is the code that will be generated by the assembler. So first instruction that will be added by the macro assembler is called the push EBP. This is called the base pointer register. So this is 32-bit base pointer register. It will be pushed inside the it will be pushed inside the stack, its value. Then move ESP or stack pointer value to the base pointer, and then stack pointer will be assigned a new added with the -8. So why we add this -8 to the stack pointer and so on, we will discuss about this one. And in the end, stack pointer will be assigned a EBP, and pop is we pop the value of EBP and so on, and then return. Now this is the diagram of this bubble sort algorithm, bubble sort procedure. What will happen here is that first of all, when we call the procedure, it will store the return address. Now one thing you must remember here, the stack is growing in this direction, like in the downward direction. It means our memory is like FFF. This is the final address whatsoever is the, and this is the 000 and so on. So our stack always grows in the upward direction, or in this case it grows in downward direction. It means the starting address is at this point. Or when we write a stack, it always grows in upward direction. So don't be confused, either it grows in downward or upward direction. It means we are decrementing in our addresses, and we are moving in the direction where addresses are decrementing. So here is the final address. For example, if our stack starts from here, then return address will be stored, and then stack pointer will be decremented, and then for example is F00 and 1 or 00 whatsoever, or 006 or 7 whatsoever the value is, F006. So return address is 4 byte, then it will be F00 and 2 and so on. Then there is a EBP and so on, then it will be E something like this one, and then temporary storage or temporary value, TEMP variable, local variable will be stored, and then the swap flag will be stored. Now why we used EBP? The main purpose to use EBP is that EBP is used to explicitly access these local variables and also the parameters that are being passed as an argument inside the procedure. Now here you can see we can access those local variables either by using the ESP or by using the EBP also. So first of all, return address has been stored. Next is EBP is stored. Third one is temp. Now for example, right now EBP has this value. When we store EBP, at the same time what we are doing, we are transferring the EBP, we are assigning EBP the value of ESP. So now the value of ESP was here because we pushed EBP. Now EBP is assigned the value of a stack pointer, so this is the value. This is the value which is being stored inside the EBP. Now if I say EBP -4, it means I can access this variable. EBP -8, I can access this swap flag and so on. So in this way we can access these two local variables either by using EBP or by using the ESP and so on. Now this is the one of the phenomenon which you will see in the coming slides, most useful when we use the local the parameters. When we pass those parameters inside the stack, we will use EBP, and EBP will have the effective way, will represent the effective way to access those local variables and so on. Now before going to further move our discussion, first we will discuss about the registers versus the stack parameters. Now either registers are better to pass arguments than the stack parameters. So register parameter require dedicating a register to each parameter. For example, if we pass 10 parameters, or if 10 parameters are being passed, then we have to reserve 10 registers that must hold that value, so that values will be used inside the procedure. For example, this is the starting of the procedure, and here are registers. So we have registers here. So register 1, 2, 3, 4 and 5 are so the registers are, and this one is a procedure. What we do if we want to pass parameters, we assign those parameters values, or if we pass arguments, we save those arguments inside the registers, and definitely these registers are accessible inside the procedure. So what we do, we assign all those arguments that we are passing inside the procedure into these registers and then use those registers. However, stack parameters are more convenient. What we can do, we can reserve an area inside the stack, and that area we store those parameters, and we can use those parameters inside the procedure. So there are two ways. I think if the number of parameters increase, for example, we have 50 parameters, 10 parameters, 20 parameters, and so on, then how we can pass those parameters as an argument, or how we can have all those registers where we can store. So stack is very easy. We can push all those parameters inside the stack, and then we can call them, we can pop them according to the order, and so on. So that is the reason stack parameters are more convenient than the register parameter. So imagine two possible ways of calling a dump memory. This is one of the, instead of dump memory, we can say array sum procedure. So we are using array sum procedure here. So in this array sum procedure, just you can assume an example of this procedure. So there are two ways. Here you can see inside this array sum procedure, we are calling array sum procedure. So array sum procedure is being called. Before that array sum procedure, we push AD, we push all the registers, because we are using some of the registers as a parameter. So as a parameter, like what we'll do, we pass array, address of an array into the ESI, length of an array in ECX, and type of an array in EBX, and so on, and then we are calling the array sum procedure. So these three registers will be used as an argument, and then they will be used as a parameter inside the array sum. And then if the procedure will complete its execution, then what we do, we pop all the previous values of those registers, and so on. On the other hand, the easiest way is we push offset of an array, length of an array, and type of an array inside the inside the stack, and then we pop inside the array sum procedure, and we can use those parameters. However, this stack area is being shared by the main program and also by the procedure. So there should be some technique so that we can access those parameters also. Now look at this example, like here. For example, if our array grows in this direction, in downward direction, what will happen? Initially when we push, so this offset value of this address of an array, so this offset value will be pushed. Then the length of an array, for example, the length of, so length will be pushed, and then type will be pushed. And when you are calling a procedure, it will push one thing. It's called the return address. It will push the return address. So now it will push the return address, and then what we can do is, maybe there are some other inside this array sum procedure, maybe there are some other and push and pop operations, and so on. So we can use them here. However, if we want to access, definitely we are passing those parameters, we are passing these three values, and we want to use them. There should be an efficient method to access them. So what we do, we use EBP. First we store EBP here, and then we use the stack pointer, which value of the stack pointer at this point, which is being stored in EBP. So inside this EBP, if we plus, or if we add 8, 12, 16, and so on, whatsoever, according to the length. So type is, for example, if it is 32 or 8-bit or 16-bit, whatsoever. So we can access all these three parameters. However, if we do not use this EBP and we are using other parameters here, what will happen? Stack pointer, when we want to access this one, and if we change the value of stack pointer at this point, and if we return, then definitely if the stack pointer is here at this point, and if we return from the procedure, then there should be some return address which should be accessed. However, the return address is at this point, so it is really difficult, or we can cause a problem because there's not any address stored here. So program might be, there'll be illegal access to the other memory area and so on, because we do not have the proper address stored here. So to avoid this situation, we must have some procedures so that when program exits, we must have this return address, and also the stack pointer must point to this return area when we return back. And also at the same time, we can have some mechanism so that we can access all these parameters which we are passing. So before going to start this example, we want to discuss about the invoke directive. Now invoke directive, and even we have used this invoke directive previously. How we used invoke stdio, std out, for example, and comma, we have some parameters like address of some variable that we want to print. So this is one of the examples that we have used. So this invoke directive is used is a powerful way replacement of for the entails call instruction. So we can use invoke directive instead of using the call one. Inside the call, what is the difference between these two, we'll discuss right now. So this invoke directive has the one way that lets you to pass multiple arguments. So that will give you the liberty, or that will give you the ease to pass these parameters, pass these arguments when you are calling a procedure. Here you can see this is one parameter that you are passing when you are calling the std out and so on. And this call instruction, you cannot pass parameters, arguments. However, if you want to pass arguments, first you have to push all those arguments inside the stack, and then you can use the call instruction. So the syntax of this invoke procedure, invoke directive is, we first have to write the keyword invoke, then the procedure name, and then the argument list. So if you are using multiple arguments, they must be separated by the comma and so on. So argument list is an optional comma delimited list of procedure arguments. So if you want to pass the arguments, they must be separated by comma and so on. These arguments can be immediate values, integer expressions, and so on. So these arguments can be immediate values or an integer expressions and so on. Variable names, addresses, and address expressions. So we can use this address keyword and so on to calculate the address, and we can use the register names also. Just like inside the there was another example. If we use invoke dw to a, and then we use eax comma and then address of some array and something. So double word was changed to the ASCII and so on. So whatsoever was in EX, it was converted to the ASCII and so on. So there are multiple. So here we use register name, and then we use address and so on. So address and so on. So register name can be one of the arguments and so on. So this is one of the example, invoke example. So here invoke directive has been used. For example, we have these two variables, byte-val and the word-val. So in this example, we are going to call a sub1. Sub1 is a procedure. Byte-val and word-val, these are the two values, two names of these two operands are being passed. First operand is a byte-val, second one is a word-val. So we are calling the sub1 and passing these two values of the byte-val and word-val. If we want to pass the address of a variable, how we can pass, you can see in this example of sub2. So we call invoke we use invoke directive sub2 and then address of the byte val and so on. So address where this byte val has been stored. So byte val, this is the data area. So byte val is 1 byte, and there should be some F0 X F000 or 1 whatsoever the address is. This address will be passed inside the procedure. Now it's possible you can pass the register name and integer expression also. So this is another example. We use invoke sub3 or subroutine 3 or procedure 3, and EAX is register name, and this is the expression which will be computed and will be passed inside the procedure. And then the fourth example is we are passing the indirect operand. So this EBX has the address. That address is pointing somewhere else. So this is the address expression. If you want to pass address, we are using, actually we are passing the register value, but this register value already has some address and so on. So we can use the this type of operand, or this type of operand that should be passed inside the subroutine and so on. Now this address operator will return the address. Now depends. This return it will return a near or far pointer to a variable. Now near and far depends on the small or the memory model that we are using. So depends on the which memory model your program uses. For example, small model, it will return the 16-bit offset. Large model, it will return 32-bit segment or offset and so on. And flat model, there is only 32-bit offset. For example, here you can see my word is a word, and there is no it's not assigned any value. And in code we use invoke, my sub, and address. So the address of my word will be passed to the my sub. So it depends which memory model you are using. In some memory models, the stack pointer is part of the code and so on, and in some other memory models, this stack is separately defined, or it has been assigned as a separate segment and so on, and can be used as a pointer variable, or can be used as a base plus the offset address and so on. So this procedure directive declares a procedure with an optional list of named parameters. Now these list of parameters we can define also here when we define the when we declare the procedure. Syntax is we use label. This is a procedure name, so this is the name of the procedure that we are using, and then procedure directive, and there is a parameter list. So in this parameters list is separated by the commas. These are the parameters that this procedure will accept as an argument. So this list is separated by these commas, and each parameter has the following syntax, the same syntax which we use when we are using the local directive. Now these parameter names include the parameter name and colon, and then we have type. So this type can be any type, like the byte, sign byte, word, sign word, double word, and so on, or it can be a pointer to any of these types and so on. Here you can see if you want to use procedure directive and with some parameters, so this is another alternative format. That alternative format permits the parameters to be one or more on separate lines. Like for example, if you want to define these parameters on a separate line, then what you can do, you use comma here, and then parameter list goes here. So these parameters can be on the same line. So all these parameters can be like parameter 1 and then its type, comma, parameter 2 and its type, and so on, and parameter n and its type. However, if you want to define multiple parameters on multiple lines, how you can use that one? The same procedure, label, comma, procedure, label or the name of this procedure, comma, so label, procedure directive, and comma, and then parameter 1 and type 1, comma, parameter 2 and type 2, comma, and so on up to parameter n and so on. So you can use these you can define parameters inside the procedure directive. In our previous lecture you have seen that we have used procedure directive, however we did not use any parameters that will be accepted by the procedure. So here you can use this procedure directive along with the parameter list, and you can define those parameters maybe on the same line where the procedure is being declared and so on. Either you can break them on multiple lines and so on. So add two procedure, for example, this procedure will add two variables, whatsoever the two variables you are passing as an argument. So this is val1 and double word, val2 and double word, and so on. So both are double word, and these two are received by the procedure as an integer parameters, and their values are double word type, and this procedure will return back the sum or addition of these two parameters into the EAX register. So this procedure will receive two parameters, val1 and val2. So procedure name and then procedure directive separated by commas, then val1 parameter is type, and so on. Here what we do, move EAX val1 and then we add val2 into the EAX. Definitely initially val1 is inside the EAX. Now we are going to add both, and again result will be inside the EAX, and we say return. If it will return from this procedure, what will happen, the EAX will contain the list of the sum of those two variables. Now this one is the fill array. Inside this fill array example, we are using the procedure directive along with the parameters that will be used by this procedure. So this fill array is going to receive the byte that will be filled inside the array. So here you can see, so this fill array receives a pointer to an array of bytes and a single byte fill value that will be copied to each element of an array and size of an array. So there are three things that we will receive. The address or pointer to the array. This is the starting address. Then we have the fill byte, and this is the array of type byte. So fill byte, the value that we want to fill inside an array, and so on. And then we will have the length of an array. What are the maximum number of elements inside this array? So we have these three parameters that will be received by this procedure. So whatsoever you will pass, this will be a pointer and byte. So P array will receive the address, and this will receive the value, fill byte value, and this will also receive the value. So array size will receive also the double word value. So what is the size of an array? Now the first thing is, we have the array size, we put inside the ECX, and we will use this ECX inside the loop. So every time loop will repeat itself, the ECX will be decremented. When ECX is equal to 0, loop will exit, and so on. So we are transferring or moving the value of array size into ECX. Then ESR has the P array or the pointer to the array. So address of this array will be moved to the ESI. Now what we are going to do, an AL register will have the fill val. So what we have to do, we have to transfer the value or the fill value into this address, and we increment ESI. Now incrementing ESI means we are incrementing 1 byte. In case if we have the ESI or this array is of type word or double word, then we have to add those sizes inside the ESI so that we can move toward the next element. So for example, initially array is like this one, F000, 001, 002, and so on. So initially ESI has got the same value like F000 and so on. When we increment, ESI will point here, then ESI will point after the next increment. So it will be like F001, and then it will be F002, and so on. So we can fill these values fill the predefined value inside the ESI. So ESI incrementing, in case if ESI is of type word, then definitely we cannot increment only, we have to add 2 inside the ESI. In case it is double word, then we have to increment, we have to add 4 into the ESI and so on. So here is ESI, and we are going to fill all these elements until and unless the ECX is equal to 0. So we are going to fill all these values, repeating this loop until the whole length has been filled, and in the end we return from the procedure. So this is one way you can see we can pass parameters, and we can define parameters inside the array after this procedure directive. And here you can see we have the swap procedure, and inside the swap procedure there are two pval x and pval y. These are the 2 pointer type, they have the addresses. So for example, if we want to change the value, for example val1 is of double word type, and there is some value, and val2 has also the double word type, is of double word type. And now what we want to do, we want to extend the value or swap the values of val1 and val2. So what we want to do, we want to swap the values of val1 into val2 and val2 into val1. So instead of using the real values, what actually we want to swap their values, so we need the addresses or actual memory area or memory location where these values are being stored, are being stored by the val1 and val2, so that we can change those values. And in the main program, if you access these val and val2, their actual values must be swapped and so on. So for that purpose we need pointers, or we need addresses where these x and the first parameter and the second parameter are being stored. So here you can see the read file is another procedure where what we can do is the buffer area, which is being used as of type pointer byte. So here in this one we can swap, in this one we can read the file and so on. So file handle is a double word, so there should be, these are the parameters that you are passing. Here there's only one parameter, and then we have local variable that we are using. So file handle is a one variable that is being used as a local, and pbuffer is a pointer to the buffer area from where we can read which holds the file data and so on, from where we will read the memory and so on. When we move from the or exit from the procedure, we use return instruction. We have seen this simple return instruction. Now this return instruction, this pops the stack into the instruction pointer. So EIP or instruction pointer, this is the return address. The return address is popped and moved towards the instruction pointer or the program counter, and control is transferred to the target address. So that is the purpose of this return instruction. Pop the return instruction from the stack pointer and stack, and moves to the instruction pointer and transfer control to that target address. Now there is another one, is return n. This n is optional operand n. It causes n bytes to be added to the stack pointer after EIP is assigned a value. This is one advantage. What is the advantage? We will discuss right now here. So why we need this n, we will discuss in the maybe 1 or 2 slide after one, why we need this n. But you just keep in your mind that when we call return with n, stack pointer or ESP or SP will be added n bytes, So this n bytes addition inside the stack pointer is more important. What is the use of this one, we will discuss. So there is another one is called the proto directive. This will create the procedure prototype First one is the label. This is the name of the procedure, then prototype, and these are the parameter list. So how we can do that one in C or C++? We define procedures. We first declare define the prototype before void main, and so on, before void main, and then after this one there is a procedure itself. We declare the procedure here, and we call the procedure, we use this procedure here and this side. So we have a prototype, we have the prototype here, and actual procedure is here. So this is the actual procedure declaration and so on. Similarly, the proto directive defines the prototype of the procedure. So every procedure called by the invoke. So if you want to use invoke directive to call any procedure, these procedures must be defined, their prototypes must be defined before calling them. So every procedure called by the invoke directive must have a prototype. Otherwise you will receive and get an error. A complete procedure definition can also serve as its own prototype and so on. So here you can see the prototype directive. There is some standard configuration. So proto appears at the top of the program listing, invoke appears in the code segment, and the procedure implementation occurs later in the program. So inside the code, this is the code area, and here is the my sub area or the procedure area. This is the main program area, and before this main program we define the prototype. So my sub is the name of the procedure. We define procedure, and the proto defines that this is a prototype of this area, this procedure. And here you can see we invoke my sub. So we are calling this my sub procedure, and then my sub procedure is defined here. So this is one of the example how you can use this proto directive. The example here you can see, in previous example there was no list of parameters that you are passing towards the procedure. Here you can see array sum procedures prototype is like this one, array sum proto, pointer to this as a pointer is a double word and so on, and array size is the double word also. So these are the two parameters that will be received by this array sum procedure. So you can define the parameter list along with the procedure name inside the prototype. And there are two things: one, parameter passing by the argument passing by value, and by the reference and so on. When a procedure argument is passed, by a value, a copy of 32-bit integer is pushed inside the stack. Now here, if we say invoke sub1 my data, so my data is already defined. When we call this invoke, a copy has been pushed inside the stack. Here is one, the MASM generated code. So it will first, what does it will do? It will push my data, and it will call the sub1. So first it will push. Now the main and important thing that we will discuss is about the return n. That I already told you why we need this return n and so on. So first we push my data, and then call subroutine 1 and so on. Then this is the next example. Here you can see my data is word and so on. So this is another example. This is 16-bit value. So this 16-bit value will be pushed before we, so this is push my data. Whatsoever the value is, either this is 8-bit value or 16-bit value, it will be pushed inside the stack first, and then it will call the procedure. So here you can see, when we use invoke, we are passing arguments. So these arguments will be pushed, whatsoever the list of arguments is, it will be pushed inside the procedure, and then it will be used inside the procedure. Now the third one is by reference. By reference means actually we are not passing the value, but we are passing the address or reference address which refer to this actual value. So we use ADDR address directive, and it will actually push the address. So here you can see it will use the one instruction called the push offset of my data. So address will be pushed inside the stack, address will be pushed, so here will be address, and then we will have the return address and so on. Then we will have the EBP base pointer, and then so on. If there are some local variables, if you push them here, they will be pushed here inside. So there is parameter classification. You can see we have input parameters, we have output parameters, and input and output parameters. Input parameter is a data that is passed by a calling program to the procedure. So these are some values that are being passed from the main program to the subroutine or the procedure. The called procedure is not expected to modify the corresponding parameter variables. So we just pass the values. So these values are being used by the procedure. However, the actual variables, their values are being actually their values are not being changed, but these values are being used by the procedure, and this procedure is not expected, or it will not change or modify the corresponding parameter variable. And even if it does, the modification is not confined to the procedure itself. Okay. Then the output parameters. The output parameter is created by passing a pointer to the variable. So we pass the pointer or the address that is pointing to the variable inside the procedure when we call the procedure, and this procedure does not use any existing data from the variable. However, it will fill a new data inside that variable, and it will return the exit from the program. So what will happen, we have one variable, for example variable 1, we pass its address inside the procedure, and inside the procedure we are modifying this variable 1 area or this value by any other value here inside this one, and it will exit from the return from this procedure. And what will happen, only the new value inside the variable 1 will be available. So this will work as an output parameter. And input output parameter is combination. So we are passing the parameters, or we are passing the arguments, or maybe their addresses. So the procedure is using those values which are being stored, and also procedure modifies those values as well. So it's a parameter, is a pointer to a variable that containing input that will be both used and modified by the procedure. So for example, we have variable 1 and variable 2, and we are passing their pointers, we are passing their addresses inside the procedure. So procedure is using those values, maybe they have some values here. These values are being used, and maybe they are modified, their values are being modified inside this variable 1 and variable 2. So these parameters or these variables are being used, their values are being used, and their values are being modified by the program. Now this is the procedure. This procedure will exchange or swap the values of two variables that we will pass them. Now here you can see we have this swap procedure, and this procedure exchanges the values of two 32-bit integers. These integers are p-val x. So we will have any other variables, whatsoever the variables we are using, and this procedure is going to define two variables like p-val x and p-val y. So do not change the values, but integers they point to are modified. So we are defining two parameters here, p-val x and p-val y, and this procedure it uses these two EAX, ESI and EDI registers and so on. This procedure will exchange the values of two variables. So this procedure exchanges the values of two 32-bit integers. It is using two local variables, or it will accept two parameters, p-val x and p-val y. This p-val x and p-val y, they do not change the values. However, the integers they point to are modified. So whatsoever the values are inside p-val x and p-val y, actually these are the addresses that will be passed inside these two parameters, p-val x and y. And now what will happen, we are going to change these two the values which are being pointed by p-val x and p-val y. So these values will be exchanged. So what will happen here, you can see the procedure. So swap procedure, we have the uses directive. We declare or we define that it uses 1, 2 and 3 procedures, and we have these parameters. P-val x is a pointer, double word, p-val y is a pointer of double word, and so on. So there are 2 parameters, and uses will define that there are 3 registers that are being used, and so on. So what will happen, EAX, ESI and EDI, they are also being pushed. P-val x and p-val y, they are also being pushed inside the stack. However, here you can see, so move ESI will have the pointer value or the address that is being stored inside the p-val into the ESI, and EDI will have the value in the p-val y. So now ESI and EDI, these 2 registers have the pointers or they have the addresses which are being used or which are being stored in p-val x and p-val y respectively. And now what we are going to do, EAX will hold the value of ESI. So for example, this is the address, I can write it here, for example, so double word, for example, F0000 and F000 and 4. So these are the 2. First address, this is stored in, for example, p-val x. Actually this one is going to show val 1, this one is val 2 and so on, and p-val y is pointing, our pointer is being stored in p-val y F004. Now ESI has the same value. So for example, here is 2 and here is 4, for example. These are the 2 values which are being stored. So here we say EAX and the value which is being stored at ESI. So EAX will have the value which is being pointed by the ESI, that is 2. And then next what we use exchange instruction, exchange EAX and the EDI. So the value of EDI is pointing to this one, EDI is pointing here, and ESI is pointing here. So now we are going to exchange the value. So EDI, that is pointing to the value 4, so it will be exchanged here inside the EAX, and 2 will be changed here. So this will contain 2 and EAX will have the 4. And the next thing that we are going to do here, the value which is being stored in EAX is being passed to the pointer ESI. So here ESI is pointing here, so 4 will be stored inside that location, and then we return back from this procedure. Now what will happen here, you can see before returning this one, actually these 2 memory locations, their values are being swapped, and now if the val 1 was pointing to this one, so val 1's value, new value is equal to 4, and val 2's new value is equal to 2. So this is one way you can use or you can pass these parameters. Now the troubleshooting tips, you can see whatsoever you do, be careful inside the procedures how you can troubleshoot. First of all, save and restore registers when they are modified by the procedure. This is one of the most important thing. For example, except a register that returns a function result, so you don't need to save and restore, because if you restore the value for that register which returns the value, for example, sometimes EAX register or the accumulator register has some value that must be returned back to the main program, so don't use those registers or don't pop those registers before returning, so on. So you should be careful. When we are using invoke, be careful to pass a pointer to correct data type. In case, for example, invoke has the, for example, in the procedure you are defining double word, and then you are defining a word and so on, and a byte. And if you are passing wrong data type or wrong pointers, then what will happen? MASM does not distinguish between the word and double word and so on arguments, and a pointer byte, so on. So they will have the wrong values when you are using those pointers and so on. So be careful. In the invoke directive, you must pass the accurate data type pointers, otherwise you will receive a wrong answer. Do not pass an immediate value to a procedure that expects a reference parameter. For example, in case of reference parameter, there should be a pointer, because we are going to refer that area. Or if you pass the value like 100 or 101, it will be considered as an address. So dereferencing its address will likely cause a general protection fault. It means if we are expecting some memory address is 0f1010, and you are passing, so we have to refer to this address, and you are passing 0002, for example. There is no 0002 address. If you are moving to this address, you are accessing a wrong memory location. Maybe that memory location is used by the main operating system and so on, so there will be protection fault and so on. So but be careful. Now, stack frames. So this is more important thing that we discussed in the few slides. When we pass parameters or when we call a procedure, either we push parameters, either we pop parameters, and we use return instruction with some number. Why we use return instruction, why EBP is being stored, that will be discussed right now. Before that one, we have two topics that are just like to recall the general concepts like memory models and language specifiers and so on. So a stack frame that we are going to discuss right now. This stack frame is known as an activation record. Inside the stack, there's a return address when we call any procedure. However, there is some area including this return address and so on. This is called the activation record also. That is called the stack frame. So the area of a stack set aside for procedure's return address and the pass parameters, saved registers, and local variables. So all this whole area, which includes these saved registers, pass parameters, return address, and so on, and the local variables. This area is called the stack frame or the activation record. This is created by the following steps. One thing is when you are calling a program, when a calling program pushes arguments on the stack and calls the procedure. So as we discussed, when we call a procedure and we push something, push some parameters before calling, or sometimes we use invoke procedure name along with the parameters. So it is being converted into this format. First, it will push all these parameters, and then it will call this procedure and so on. So the called procedure pushes EBP on the stack and sets EBP to the ESP. Sets EBP to the ESP and so on. So this is the way, as I told you, EBP will be used to access this new area or this area inside the stack and so on. So here, if local variables are needed, a constant is subtracted if we are using local variables. So we can access all this area by using the EBP. So EBP is also there. EBP is also stored here. So now first EBP, we are going to push EBP, and then next thing is EBP is assigned the value of stack pointer. Maybe we add some other values or parameters inside the stack. However, EBP, we know that EBP is the next before this EBP return address was pushed and so on, and we know that this occupies 4 bytes, and then if we subtract 8, then we can come here and we can access this 4 byte and 1 byte and whatsoever the number of whatsoever size value we pushed inside the stack and so on. So we can subtract something from EBP, some value from the EBP, and we can access the area inside the stack and so on. Here you will see, before going to see the example, we have some memory model. We have already seen this one memory model. So a program's memory model determines the number and size of the code and data segment. So real addressing mode supports tiny, small, medium, compact, large, and huge. So in real addressing mode, we have the stack pointer, program counter, and so on. We have the segments. The segment registers along with the pointer register are base and the segment register and so on, and the pointer are offset registers. Their combination will calculate the effective address. However, the protected mode support only by the flat model that we are using. What is difference between this one? In the small model, the code is 64 kilobyte, and it including the data. Data is less than 64 kilobyte, and all offsets are 16-bit. So code is less than 64 kilobyte. Data including the stack is also less than 64 kilobyte, and all the offset are 16 bits inside this small model. So if you use huge, this size increases. However, we are using the data and the stack, they are in the same area and so on, and they must be less than 64 kilobyte in case of small. In case of flat memory model, the single segment for code and data up to 4 GB is being used, and all the offsets are 32 bits. Now model directive, as we already know, that model directive specifies the program memory model, and we have the memory model option, and then we have the model options, so on, and the language specifiers also there. So memory model can be of the following, like tiny, small, medium, compact, large, huge, and so on. Then model options include the language specifier. Here is the language specifier. Either we can use C, Pascal, and so on, and also we can use std call. So these are the language specifier, how we can pass parameters, how these parameters are being stored inside the stack, and so on. So these model options include the language specifier, and this language specifier defines the procedure naming scheme and also parameter passing conventions, how we can pass parameters and how these parameters are being stored inside the stack. Now you can see, if you use the C as a language specifier instead of using std call, the procedure arguments are pushed on the stack in reverse order. For example, we have procedure name, comma, parameters or procedure arguments. There are multiple arguments. So argument number 1, argument number 2, and argument number 3. So these arguments must be pushed inside the stack. So first, this last parameter will be pushed first, then this parameter will be pushed, and this one, and so on. So this is the third parameter, second parameter, and the first parameter, and so on. Then we have the return address and all these things that will be stored. And the calling program cleans up the stack. So when we are exiting from this procedure, this area must be cleaned, which we are using, which is being used for storing these arguments. On the other hand, this Pascal, if you use the Pascal language specifier, the procedure arguments are pushed in the forward order or from left to right. Means the first parameter will be pushed first, second parameter will be pushed second, and third parameter will be pushed as the third. So these arguments 1, 2, 3, they will be pushed from the right to left to right. So I mean the first argument will be pushed first, second argument second, and third argument third. And cleanup procedure cleans up this stack. So all these procedures are being cleaned by the clean the stack area. If we use a steady call, this is same as the C calling language specifier. So procedure arguments are pushed on the stack in the same reverse order as being the C, the language specifier, and so on. So just keep in your mind, if you are using the C language specifier or std call, they are being stored in reverse order. It means the last argument will be pushed first, second last, and then this one in the reverse order from right to left. So now is the main discussion about the explicit access to the stack parameters. Why we need to store a base pointer inside the stack. Now we are discussing about the explicit access to the stack parameters. That why when we are going to push arguments inside the stack and we call the procedure, there is a return address and a stack pointer is pointing somewhere else to the new area. We cannot change the stack pointer, because if we move on the top side, for example, these are the arguments that are being passed, and here is a return address, and a stack pointer is somewhere here, for example. So if we want to access them, definitely we decrement the stack pointer and so on. So what we do, so a stack pointer will be decremented. If you add or decrement in the stack pointer, then definitely by using push and pop operation you can increment and decrement in the stack pointer and so on. However, if I want to access these 4 areas, or the 3 or 4 variables or arguments which I stored, then definitely we will miss this return address, that what was the return address when we return from the procedure. So we need alternative method to explicitly access these stack parameters. A procedure can explicitly access stack parameters using a constant offset from the EBP. So EBP is the base pointer in real addressing mode. So we use a constant offset with the EBP to access these parameters that we are storing inside the stack. So EBP is often called the base pointer or the frame pointer because it holds the base address of the stack frame. So this base address is stored inside the base pointer, or so this whole area is called the stack frame. So a stack frame is stored here. Now EBP holds the base address. Now if we want to, so this can hold all these parameters, all the registers that you push and so on, and then we can access them by using the EBP or the base point register. EBP does not change value during the procedure, so you cannot change the value of EBP during the whole procedure. So it will have the constant value, and that value is actually the value of a stack pointer, the old value of a stack pointer. We'll see in the next example. If you change this EBP, definitely you cannot access these values. It's not possible. So EBP must be restored to its original value when the procedure returns. So when our EBP has main function is to access these values. Now if we return, then definitely we have to return back the original value, because EBP might have another value that might be used by the main program and so on. Now here you can see this is the stack frame example. Now this whole area is the stack frame. We have this double word sum. Okay, we have the code. What we do, we call add2, and add2 is a procedure. First we push 6, push 5, and we call add2. So first this argument is being stored inside the stack pointer, inside the stack. So this is the stack area. Stack starts from here. When we push here, this value will be pushed, a stack pointer will be incremented and so on. Again we perform another push operation, and then when we call this procedure, the return address will be pushed here. Then next what we do, we push the EBP, and this EBP is pushed by when we call this procedure. And after pushing this EBP, we are assigning a new value to the EBP, that is called the ESP. Now ESP and EBP, they both are pointing to this area. Now for example, if we want to access this value, we can access either by using ESP, but the problem with ESP is you can change the value of ESP. If you change the value, then ESP will point here, maybe ESP will point here to access these values. However, if you return back whatsoever the current value of ESP is, it is being expected that this, when we return from the procedure, ESP must point to the return address. So instead of using this ESP, we are using the EBP. Now this address or this instruction will point or will assign the value, its current value, to the EBP. So whatsoever the current value of ESP is, it will be moved to the EBP. Now ESP is pointing here. Now if I want to access the address, I will plus 4. Actually, as I told you, if the stack grows in this direction, this is the 000 addresses, and this is direction is the FF addresses. So our stack grows in downward direction, or in the direction where our memory decreases, our memory addresses decreases, and so on. Or you can use the same naming convention here. So stack pointer first is 0006, all these zeros. Then we have 000 and 5, and so on. Then we have the return address. Then we have EBP value has been stored, and so on. So our stack grows either in this direction, and this is the 000 and 0, so on. This is the address, and addresses are increasing in the reverse direction, as we have discussed in the previous our previous lectures. So this is the growing direction of the stack. So both are similar. There is no difference. So for example, if the address is F00 and F and so on, then we have this one, this address start from the F00 and the BRE. So A, B, C, D, sorry, this should be B, for example, B, C, D, E, F, and so on. So 4 bytes are being assigned here, and then 4 bytes are being assigned here, and so on. So this is decrement inside the addresses. So now we will discuss why we need to use this EBP. So suppose this one is F00 and A, and this should be F00, and this should be 7, or maybe 6. So 6, 7, 8, 9, and then we have A, and so on. So here is, for example, we have the F00 and the 2, and so on. So if we want to access this one, what we have to do, so the current value of EBP is, like for example this one, this should be for example the EF01. okay, so E or B, whatsoever the value, D or E. So if we want to access this area, by using the EBP, so how we can access, if EBP is now right now, like for example pointing here at this point, so if we add 4, then definitely we will access this area here, and if we add 8, then definitely we will access this area. If we add 16, or sorry, the 12, we will access this area. So we can access any of these values by using the EBP. So now one thing, we can access these areas inside the stack. This is the activation area. So all these parameters that are being stored, like 6 and 5 that are being stored, we can access them. However, if we return back, definitely a stack pointer must point this area, because this address is required when we return back from the stack. However, we must have to clean this area also inside the stack. If we do not clean this area, then our stack will grow every time we call the procedure. So here are only 8 bytes if we are going to push 2 double words. However, if we push 4 double word, 5 double word, and we call 100 times the procedure, then all this area should be cleaned. Otherwise, the problem. So when theoretically we need this return address also, along with we have to move the stack pointer 8 bytes backside or at the back end. How we can do that one, you will see here. So this is the add to procedure. So add to procedure is like this one. So we have 2 parameters here. You can see there are 2 parameters. So this is similarly to the previous one as we have seen this one, and we have the return value. So this add to procedure, as you have seen in the previous slide here, has the same value, but here it will be added these four lines. First, it will have the push EBP, and then EBP is assigned the new value of ESP, so that we can access these 2 double words, or val1 and val2, and then in the end we will have to pop up. So this leave instruction is similar to move ESP or EBP. So ESP is assigned the previous value, whatsoever the previous value was. For example, what will happen here, I can draw at this point. So 2 double words will be added here. First one is the val2, the address of val2, the first address, the value of val2, and then val1. Then we will have the return address, and then whatsoever the value. So EBP is stored here. So we will have EBP. So val2 and val1 and so on. Now what we need here, we can access these val1 and val2 by, so EBP was stored, and similarly EBP is assigned the value of ESP according to this instruction. Instruction number, for example, 1, 2, 3, 4, 5 and 6. So according to instruction number 2, this ESP value, when it was here, it will be point to this one. ESP will be, a value will be assigned to the EBP. Now you can add other values here inside the stack. A stack will grow in this direction, for example, and when you will come here, so previous value when a stack was here, it is inside the EBP now. If the stack grows, it doesn't matter, but we already know that what was the value of a stack pointer when a stack pointer was here, because we know that we already pushed EBP, and now EBP holds that value, because that value is required to access val2 and val1, and also we know that there is a return address also. So what will happen here, we can access, we have stored push EBP, and we have the ESP and so on. So up to this point our stack looks like this one. Now when we perform all these operations, so EAX has a value, we perform addition, and now EAX has the sum of all. So fourth instruction will store sum inside the EAX. Now before leaving this whole procedure, as I told you, we have to clean up this area also. What we are going to do, now ESP is at this point. First thing is, we want to move ESP, maybe ESP's value is somewhere here. ESP is being moved with the EBP. Why we need this instruction? Because now a stack pointer will have the value when a stack pointer was here, the old value which was stored in the EBP. So now a stack pointer will have the old value when it has pushed this EBP. Now a stack pointer will point here. If we perform pop, this EBP value, whatsoever the previous value was stored in EBP, will be again restored or popped back inside the EBP. Now we have this return address. Now stack pointer will, after this pop operation, stack pointer will be here. Now when you return, then definitely we have the return address. We have the return address. So this return address, after this one, this return instruction will, instruction pointer or EIP will be equal to this return address. Now this 8 is the value that will be added into the stack pointer. Why? Because we are using these 8 bytes of this stack, because when we started our program, our stack pointer was here. This is a starting point from where our stack has started growing. Now currently when we return, then definitely our stack pointer will be here at this point, and these 8 bytes have been used. So what we have to do, we have to add ESP plus 8 so that stack pointer will move here. So this will be the original value where our stack pointer was. So all these spaces will be freed up, or they will be, their values don't mean to, they will not occupy any value or any space. Actually what we are going to do when we return back, we are going to completely free this area which is being occupied by the procedure. Otherwise what will happen, if we do not use this 8, or if it is not being used by automatically by the machine, what will have, once you called, these 8 bytes will be used. Again in the next call, these 8 bytes will be used. Again third call, 8 bytes will be used, and so on. So in each call, if you are again calling this procedure which is using 2 parameters of 8 bytes, 2 parameters, and the total size is 8 bytes. So in every call you are occupying 8 byte memory location. Suppose if you are calling 1000 times, so 1000 multiplied by, so it should be 1000 multiplied by 8 bytes. You are occupying this much size of this stack. Definitely you will get some error because stack has some limitation. You cannot exceed some limitation. So this is one way you can clean up the area which you are using. So this is add sub procedure. You can see this add sub procedure. So how we can access, so add to, we have add to procedure, so we are adding this one. Another way is, in our previous example you have seen, so we can use EBP. You can see here the next parameter is 6, the first parameter is 5, so second parameter is being stored here. First parameter is stored afterward because we are storing from in the reverse order. If we use the C or std call, language specifier, and so on. So the right side, the second parameter is being stored first, and then the first parameter, then return address and EBP. So what we do, EBP is being pushed, ESP, whatsoever the value of ESP is here, that will be stored inside the stack the base pointer, and previous value of base pointer has been stored here, and now EBP has a new value. That value is the ESP, and so on. Now EBP, we know that EBP has the stack pointer value. If we add 4, we can access this address. If we add 8, then we can access this area, and so on. If we add 12, we can access this area. So instead of using their names or the procedure names, we can use, or the parameter names, we can use EBP plus 12 and EBP plus 8 to perform these addition. And this is the leave instruction which will move the value of stack pointer to the base pointer. Sorry, move the value of base pointer to the stack pointer and pop EBP, and return 8 will get the return address along with the sub addition of 8 inside the stack. So the stack will point here at this point. After returning, ESP will point here. If we do not use this 8, stack pointer must be here. So these 8 bytes have been wasted. So this return 8 will add 8 inside the stack. So now the stack will be here, because this is the decreasing order and this is increasing order here. So ESP, if we add 8, then definitely it will come here. Okay, so this is the drill example. For example, create a procedure named difference that subtracts the first argument from the second. Following is the procedure call. So push 14, push 30. So 14 will be pushed first, 30 will be pushed next, and then you can use these two parameters. Definitely here is the return address, and then we have the EBP, and we have to use this EBP as a base pointer for this activation area or stack frame, and EBP plus 8 will access this area, EBP plus 12 will access this area. So here you can see this is the automatically assigned by this one. So we can use EBP, we can use assign the ESP into the EBP. So EBP plus this first parameter is being assigned to EAX, second parameter is being subtracted from EAX, and then we pop EBP and then we return to the main program. So passing arguments by reference. Now whatsoever we were doing is passing arguments by the values. Now array fill procedure is the same. So the reference means we are passing the addresses inside the procedure. So here you can see array fill procedure. It will fill the array elements by using 60-bit random integers. So you can use either random integers or you can use the predefined integers whatsoever. A predefined integer. So it's better to use predefined integer. Otherwise you can use random procedure. So we can call a program, this program, by passing the address of an array, because we need this address of an array. So we have the count. So count is the total number of elements that are being used. So total number of elements that are inside this array. And this array is of type word, so 16-bit value will be used to fill this array. So here you can see you have seen the example. So we are passing the offset or the address inside the stack. So array fill can reference an array without knowing the array's name. So if you change the name of array, it doesn't matter. So inside this one, EBP will be stored, and we will use the move EBP and ESP, the same one. We push all these what we could call the registers. However, here you can see ESI has the EBP, this is the value, and then next one is the, so in the previous slide you can see first we push offset and then we have the count. So here actually we are going to use the offset or address, and here is the value. This value shows the count or total number of elements inside an array, and offset is the base address, the starting address of this array. So we can repeat this counter and we can add values inside this array. So this one is, as you can see, offset, and we have the count here. So we have offset and we have count. So EBP plus 8 will access the offset, and EBP plus 12 is the the EBP plus 8 will access the count, and offset will of this array will be used or accessed by the EBP plus 12, and so on. And ESI points to the beginning of an array, so it's easy to use a loop to access each array element, and so on. Here is an example of this, complete example of this array. So we push offset, push count, and array, and what we do, move ESI, offset of an array, ECX, and so on, and EBX, and so on whatsoever. So up to here, for example, we are calling an array. Inside this array you can see EBP has been pushed, ESP has been assigned. We push all the, so if we push all registers, then we pop also. So we push and pop all these registers and so on. If we push, then definitely we pop all those registers. Here you can see. So first thing is, we know that we have the ESI and we have the ECX. So we have the ESI and we have the ECX. What we do now, our ECX, compare ECX with 0. If either ECX is less than or equal to 0 or not, jump if less than or equal to 0. So if it is not less than or equal to 0, what will happen? It will not jump. If it is greater than 0, so what we do, we move some value. For example, here we are not moving the random value, but we are moving constant value, that is 0, into the ESI. And what we do, we increment the ESI with the we add the type word or type whatsoever the type of this array is. So we are actually adding 16 bits or 2 bytes, 2 inside the ESI, and loop will continue, loop L1 and so on. So either you can use this loop L1 or you can see the jump L1. And again, we if we use loop, so you can use loop 1. So ECX will be decremented again and again until all these elements of ESI where it is pointing will be filled with the value 0. If it is ECX is equal to 0, for example, inside the loop, then it will pop all these registers, pop EBP and return 8. So whatsoever this 8 means, we are going to remove the area where we stored the address or the offset of the array, and we also return the size of this array that we stored. So we are going to clear this area also. So this is the cleanup. You can see here the cleanup the stack. So it is being done by the assembly and so on. There's one instruction, load effective address, LEA instruction. This instruction returns the offset of both direct and indirect operands. For example, offset operands can only return the constant offsets. However, LEA is required when obtaining the offset of a stack parameter or a local variable. For example, here you can see inside the procedure we are using count and the local temp. So if you want to use the EDI is equal to offset of count, you will get the invalid operand. If you use offset temp or whatsoever the value is, you will get the wrong answer or invalid operand. So LEA will give you the effective address of this count or temp and so on. So temp has the address also, count has also the address. So instead of using offset, you must use the load effective address. That will give you the that will return the offset of both direct and indirect operands. And then creating the local variables, as we know that if we want to create the local variables, how you can create, you can explicitly state the local variables, subtract their total size from the ESP if you want to access them. So how you can do that one? This following example creates and initializes two 32-bit local variables. We will call them local A and local B. You can use local directive, or if you don't want to use local directive, this is another way how you can do. So push EBP, move EBP, and this is the local A, EBP minus 4, EBP minus 8. You are assigning or you are going to modify their values. So it will create two local variables. If you use local directive, then already these memory locations before this stack, like the stack frame, they will reserve this area. Otherwise you can do this one by using this EBP minus 4 and so on. So now we will summarize what we did in this lecture. In this lecture we discuss about the local variables by using the local directive, how you can use the local directive, and also in the end you can see you saw that we can define our local variables without using local directive and so on. Then stack parameters, we can use either registers to pass parameters or pass arguments, or we can use the stack parameters. Stack parameters are more simple than the register parameters, are more convenient. Then we can use invoke directive instead of using call directive. Invoke directive give us access to directly pass arguments. Then procedure directive, we can use procedure directive along with the list of parameters. Then we have proto directive. If you want to use invoke directive to call any procedure, we must define the prototype of this the procedure or subroutine before the main program, so that after that you can use invoke directive. We have seen the example of passing parameters or passing references by value, passing the arguments by reference or by value, and so on. Then parameter classification, there are input parameters, output parameters, and there are IO parameters. Then we have seen the add to or exchanging the values of two variables, and so on, and then troubleshooting tips. Then we discuss about the stack frame area, where EBP was used to point to that area. So we used EBP plus the constant value 8, 4 and something to access that area, and so on. Then language specifiers, we use C, Pascal, and so on. So how naming conventions and parameter convention they are using. They use either store parameters either from left to right, from like in Pascal it is using the forward order, and C or std call uses the reverse order. In this reverse order, parameters are being accessed from right to left, and so on. And we use EBP, how you can use EBP to explicitly access the stack parameters, and so on, and passing arguments by reference, and so on. And you can create labels without using the local directive, and so on. So this is end of this lecture, and hope to see you in the next lecture. Till then, Allah Hafiz.